Okay, so we're looking at 10.4 number 2, where we have y prime is a quarter times the matrix negative 5, 3, 3, negative 5y. And in order to do these problems, what do I start with?
God damn it. Lambda I minus A.
Okay, so first things first, I have to find eigenvectors. Well, values. Find eigenpairs. Okay, so what's the matrix I'm considering here?
What do you mean the matrix you're considering? Which, like, what is going to be the thing that you're trying to find?
Yeah, so I think I'm trying to find things that some matrix inflates or deflates by a kind of constant factor, right? I'm trying to find the eigenvalues of something. What is the something for which I'm trying to find the eigenvalues?
Negative 1/4 times that matrix y.
Okay. Wait, matrix Y.
You would just be finding the eigenpairs for the matrix itself, right? Not even the 1/4, because it wouldn't matter.
Yeah, I'm gonna leave the 1/4 out of this business.
Yeah, you would just be doing
So
A matrix. Yeah.
I'm gonna call that matrix negative 5, 3, 3, negative 5. I'm gonna call that matrix A.
Can we just do that? Just say, like, that's actually the coefficient matrix?
Yeah.
This is the coefficient matrix. Okay.
So you can put the quarters in there, but the let's see, do I need them?
The quarters?
The quarter.
I don't think you do.
I put it in there.
Totally.
I thought to the right eigenvalues, leave just multiplying the eigenvalues by 1/4 at the very end, but when it comes to finding the eigenvectors, that's when it gets all weird.
Yeah, so my concern, I suppose, is that I'm making this maybe statement that if I have a constant times a matrix A, that the matrix A has the same eigenvalues. And I don't think that's true anymore. I thought that was true intuitively for a second, but I think that might not be the case. So I'm really looking at A minus lambda I x equals 0, right? That's what it means for lambda and x to be an eigenpair.
Mm-hmm.
And if I think about this other matrix that I'm kind of considering using, which is a quarter times A minus lambda I times x equals 0, that really feels like lambda is going to be different in that case. You guys see that?
Mm-hmm.
I'm concerned that I should be maybe obviously able to do something like multiply by 4 across this thing. But I think that multiplies my lambda by 4 too. So I think actually I'm going to go back on my word and I'm going to take 1/4 times this thing to be the matrix that I'm finding eigenvalues for. I'm not completely sure that that's absolutely necessary right now, but I'm sure enough to be suspicious of myself. Does that make sense?
Yep.
Okay, so let's try it. Okay, so I need to consider taking, and you guys usually do this, lambda I minus A, right?
Yep.
And I need to take the determinant of that and then set it equal to 0, yeah? Okay, so I want let's see, so this is 2 by 2, so I'm going to have lambda and 0 and 0 and lambda minus the matrix minus 5/4, 3/4, 3/4 and minus 5/4. And then I need the determinant of this whole thing and set equal to 0. And so that's going to be the determinant of lambda plus 5/4 and minus 3/4 and minus 3/4 and lambda plus 5/4 again. Set equal to 0. I don't know why it is, but for whatever reason, everyone seems to start emailing at exactly 3 o'clock every day. Okay, so determinant of this thing is lambda plus 5/4 squared. Then what? Is this minus or plus?
Yes. Minus
9/16.
3/16.
Isn't 3 times 3 9?
Oh, it looks like you wrote a 1 there.
Should be 3. Okay. And then multiplying out, I got lambda squared plus 10/4 lambda plus 25/16 minus 9/16 equals 0. Which means that I have lambda squared plus 5/4 lambda plus, what is that, 1?
1.
Equals 0? And then what?
Factor that shit.
Okay. What do you get when you factor this shit?
-1/2 and 2. Yep. Negative. Positive. Whatever. Positive. Yeah.
So that would be a lambda minus 1/2 times lambda plus 2?
Or
That's not right.
Lambda plus 1/2 and lambda plus 2.
yeah.
No. Yeah.
Yeah. And then I see what you were saying. So that's lambda is minus 1/2 and minus 2 are my eigen. What are those?
Your eigenvalues.
Okay. Now what?
Now you have to find the eigenpairs.
Now you have to do the lambda equals 1/2 or negative 1/2 identity minus a.
Okay, so I need to take my a minus lambda I, right? And sorry, you guys do that the other way still. My bad. That would be a lambda I minus a at lambda is minus 1/2. And also at lambda is minus 2. Okay, so I need my matrix, which is, okay. So that's going to be minus 1/2 plus 5/4, minus 3/4, minus 3/4, and minus 1/2 plus 5/4. Okay, then what?
3/4,
Negative 3/4 and 3/4.
Your method.
Okay, so simplifying a little bit, first that's minus 2/4, I suppose. So that's plus 3/4, minus 3/4, and then the other one should be the same with opposite sign, so minus 3/4, 3/4. And then what am I, if I'm going to ref this, what am I augmenting by?
0.
Yeah, so what I'm thinking is, what vector does this take, right, to 0?
Yeah.
And so I'm augmenting by this 0 vector. And then the second row is always redundant, or should be. If the second row is not redundant, then something has gone wrong. meaning that you usually misfactored or dropped a sign somewhere in the finding of eigenvalues. Okay, so what I found is that 3x1 minus 3x2 equals 0, which tells me that x1 is x2, which means that my eigenpair is 1, 1. Oops, that's the wrong thing. So that's an eigenpair there. That guy. Pretty good with that?
Yeah.
I'm getting a lot of random background noise.
Someone vacuuming?
My mother's cleaning her house.
Masha?
Okay, if we could kill our mics when mom's vacuuming, that would be cool. Alright, so then when lambda is -2, I have... Oh, what was my matrix again? I'm going up and looking. Okay. So then I have -2 plus 5/4, -3/4, -3/4, and -2 plus 5/4. And again, this matrix is multiplied by something like x1, x2, and set equal to the 0 vector. And let's see, that's 8/4, pretty sure. 2 is 8/4 still. Which I think gets me to a matrix that looks like -3/4, -3/4 augmented by 0, and the same. Okay, second row is still redundant, which tells me that -3x1 minus 3x2 equals 0. Which gives me what for an eigenvector?
1 and -1.
Oops, that's not how you write vectors. Okay.
And -2 is lambda.
Perfect. Yep. So going back up, that is -2 comma 1 -1
Yeah.
is an eigenpair. Okay. Now what?
And again, it wouldn't matter if it was -1, right?
No. In fact, any scalar multiple of 1 -1 works. So you definitely get some choices in here.
Put it all into a formula for y vector.
Okay, so I'm gonna go way back up to the top here. And I'm gonna say, all right, so that means that y is C1, and then what's my vector?
1, 1.
1, 1, and that goes with e to the, what was the eigenvalue?
-1/2.
Perfect, times t, plus C2,
And then 1 -1. And then times e to the -2.
perfect. Okay, then let's do just a tiny bit of investigating while we were kind of thinking about it. So I was thinking about this using -5, 3, 3, -5, right?
Mhm.
So let me do lambda minus, or lambda I minus that. I get this guy. The determinant of that thing is lambda plus 5 squared. Minus 9, which I'm supposed to set equal to 0. So that would tell me that lambda plus 5 squared is 9. So
-2.
Yeah, so I get lambda is -5 plus or minus 3. Which seems like I'm not getting this. I'm getting lambda is either -2 or -8.
But if you throw that 1/4 on it now,
Yes. But these importantly are not the same, right? So my initial instinct was wrong. You can't disregard the constant. You need to at least drag it along with you.
So
Does that make sense?
yeah. So I came up with a different determinant and still got the same.
You came up with a different determinant.
Slightly different, yeah. Can I write it on here, like to the right?
Yeah, sure. I'm also recognizing that I did a stupid by multiplying this out earlier. I don't know why this was my first instinct. Over here. It's kind of braced in red.
I see.
That was all really quite a dumb way to solve that. From this one, I really should have just done lambda plus 5/4. 5/4 is plus or minus 3/4. It was already a completed square. I don't know why I felt the need to multiply it out and then factor it when I could have just solved for it the way it was.
Nice to meet you again, Joe.
Okay. Yeah, so Matt, what you've got over here is this thing is the determinant of I see. So this is the determinant of a minus 4 lambda I.
Right.
So you took the matrix equation where A is not the A I had. You took this kind of. Maybe let me write this differently. So you had 1/4 times what is it? This was the original matrix, yeah? Yep. Okay. So you had 1/4 times -5, 3, 3, -5, minus lambda times I, and the determinant of this matrix is supposed to be 0. And then it looks like you kind of did this sort of strange thing where you said, okay, so if this matrix here is singular, then 4 times that matrix is singular. And it's maybe not necessarily an evidence that that's true, but it is.
Right.
Yeah, so this is really a property of singular matrices, that if you have a matrix that's not invertible, if you multiply it by a constant, it's still not invertible.
Okay.
Be a little careful with that, because there's a similar sounding converse statement that's false.
Yes, there is.
Or let's see, yeah, so That's really this statement. So what you're doing is you're saying that a singular matrix, or A being singular, implies that a constant times A is singular. That's true. This kind of similar statement is not true. That say B not singular implies that K times B is not singular.
That isn't true.
No, it's only true if you assume that K isn't 0.
Okay. Yeah, I only did it this way for this one though too. The rest are all the way we did it now.
Yeah, I mean, I think so. The reason that he's writing that constant outside of the matrix is not to try to confuse you. It's just to try to make typesetting more reasonable.
Mm-hmm.
But yeah, it seems obvious in retrospect that it should have been a little confusing because you can't just look at the matrix. You do need the constant in there first.
Right.
Or at least you need to account for it. Cool. Does that... Anybody got a question on this process? Okay, cool.